Let's capture the other two cases that we need to discuss. So the other two cases are when we have the overdamped situation corresponding to two real roots, and the critically damped case when the two real roots are equal. So when we have two unequal real roots, we can write the homogeneous solution in terms of those two roots. This is the first root with a positive sign for the square root, and this is the other root with a negative sign in front of the square root. And we have these coefficients C1 and C2 that need to be determined. And so we have C1 times this exponential factor. This root corresponds to a decay in time which is slower than the decay corresponding to the second root, but both correspond to decaying solution in time with weighting factors C1 and C2. And so we now put the initial conditions on this homogeneous solution. V at 0 is equal to 1, and V d dt is equal to 0. And that gives us a system of these two equations for the two unknowns C1 and C2, which we can solve simply. And rather than bore you with details of that algebra, I'm simply giving you the solution. And it's a good check. You should do the algebra yourself and see that you get this solution that is written down here. That V of tau is given by this solution. It may look like that this is a growing exponential, but this exponential factor is to be multiplied by this factor e to the minus beta tau. And since beta is a positive number, this decay rate is faster than this growing rate, and therefore the composition of this decay times this growth is actually a decay with a positive weight here, and another positive weight times more rapidly decaying the solution when you combine these two. So overall this corresponds to a decaying solution. And finally, this case when beta is equal to 1 is when the two roots are equal, r plus and minus is equal to minus beta. And so the solution in this case we have to pay a little more attention to, because this is the case where the two roots that we had corresponding to the two homogeneous solutions have become equal, or they have become degenerate. And so we don't have two linearly independent solutions anymore simply in terms of the exponentials of r plus and minus tau. And so we need to find a second linearly independent solution. We can use these two roots as giving one linearly independent solution, C1 times e to the minus beta tau. We are calling this V1. We need to find a second linearly independent solution. And so there is a method which is a systematic method called method of undetermined coefficients, which you can read about. And this is a very powerful method. It says that if we know one linearly independent solution, V1 of t, then we can propose a second solution as some arbitrary function that we don't know, and we are going to determine such a function times the linearly independent solution that we know. We propose a solution of this form and substitute this in the differential equation and obtain a differential equation for g of t, or g of tau in the present case, and we can solve that. And this method works, and it will find us that the solution is in fact just tau. G of tau is equal to simply tau is what can be found by this formal method. And so we are skipping the details of this formal method, and in fact what we're going to describe when we talk about the solution to the particular solution with right hand side to the differential equation, the method of variation of parameters, is a more general version of the method of undetermined coefficients. So it's in that more general setting that we're going to be essentially looking at a method of this kind. So using this method, or knowing that such a solution is permitted by the differential equation, which we can verify by substitution in the equation, we can then proceed to determine the unknown constants C1 and C2. So for that, we need to evaluate the first derivative of this homogeneous solution, which is simply algebraically when we differentiate the second solution, we get these two terms. This, of course, is the obvious first derivative. And so we impose these two conditions, same conditions as we had before, and now we again have a linear system for the unknown C1 and C2, and we can solve for C1 and C2 in quite a simple way. And the solution turns out to be very nice and simple. and we can express it in this form. V of tau is exponential of tau times this factor 1 plus tau. So 1 plus tau is a factor which corresponds to growth. It starts at 1 and grows in time, tau. E to the minus tau is a decaying solution which starts at 1 and decays, and the product of these two corresponds to an overall decay starting with the solution that is given. It doesn't correspond to a growth and followed by decay for the initial conditions that are given. We start at 1 and we start at 0 slope and then decay. So let's now turn to look at the solutions in some detail, and for that we have made a plot here. Let's zoom in on this plot. So we are plotting the solution here, the normalized solution, normalized by the initial displacement against normalized time. And so the first case we are illustrating is when the value of damping is very small, and the value we have selected is gamma equals 0.01. And you can see that this solution corresponds to oscillation whose amplitude is decaying very, very slowly. We get a lot of oscillations before any significant decay happens. The next solution here corresponds to gamma which is 10 times higher, gamma equals 0.1, and we can follow the rate of decay here. And as gamma increases, the next one is gamma equals 1. You can see significant undershoot and a little bit of overshoot again around 0. The next value here is gamma of 1.5, and if you blow this up you will notice that there is in fact a slight undershoot, and so this is getting close to a critical value. The critical value is gamma equals 2 when the solution does not have any undershoot. It monotonically decays to 0, and this is what is called a critically damped condition. It has no overshoot or undershoot, and as gamma increases beyond that, in this region here we have gamma bigger than 2, and so we have plotted here values corresponding to 4, 8 and 16 for this last curve here. We have a more and more monotonically decaying solution. It seems a little bizarre that as value of gamma is increasing, the rate of decay is actually reducing. This is something that we can go back to the equation and analyze why this is happening. It's an interesting little puzzle to sort out, and it's because of the way we non-dimensionalize, because we remember in this normalized time we have non-dimensionalized this by the oscillation time scale, and that oscillation time scale is disappearing as gamma is becoming larger and larger. It's interesting that as gamma increases, the rate of decay slows down, and so this may seem counterintuitive, so it's something you should think about, and it's because of the way we had non-dimensionalized the problem that it is behaving this way. And it's also a good exercise if you want to think about an asymptotic solution, finding a solution corresponding to large gamma starting with the differential equation that we have. That problem can be posed in other ways, and we will look at some of that later on.